All right, now looking at another example here. If we take a full reaction here, making ammonia from nitrogen and hydrogen, we can calculate, excuse me, the entropy change for this reaction from the standard entropies of the material involved. So again, it'll be the sum of the standard entropies of the products minus the sum of the standard entropies of the reactants. Now, before we do the calculation, why don't we just look at the reaction a little bit. We've got 1 mole of nitrogen gas, 3 moles of hydrogen gas. It's becoming 2 moles of ammonia gas. So we're going from 4 moles of gas to 2 moles of gas. Now, less gas, that should mean that we see a decrease in the entropy. So it would make sense here if we end up with a negative number. The system's actually getting more ordered. We're taking more disparate pieces and putting them together into fewer pieces. So less disorder or more order in the system. Okay, now again, the numbers here for standard entropies, this is coming from the table in one of the appendices in the back of the textbook. So I've already looked them up for the purposes of kind of filling in the lecture notes here. So products here, 2 moles of ammonia. So I'm going to use square brackets to indicate the product term and the reactant term. Since there's 2 moles of ammonia, we're going to multiply the standard entropy by 2 because that's on a per mole basis. That in the back of the textbook is 192.5. Now again, this is all in standard entropy units, which are joules per K mole. And I'm going to leave those out as I write in all the numbers, but keep that in mind because that will be important a little bit later on, that we'll have to do some manipulation of the units. So 2 times 192.5, that's it for the products. We want to subtract the sum of the standard entropies of all of the reactants. So N2 is 191.5, just 1 mole there, so we don't need to multiply that by anything. And since we're summing, we'll add the contribution of hydrogen. So 3 moles, so we'll multiply the value from the textbook by 3. And hydrogen is 130.6 joules per K mole. Okay, so 2 times 192.5. This first term would end up being 385 joules per K mole. And then the second term, we multiply and add all that out, is 583.3 joules per K mole. So if we do that subtraction, we end up with negative 198.3 joules per K mole. Right? And that is, like we thought, that is a negative value. That means the system is getting more ordered. We go from 4 moles of gas to 2 moles of gas. We did order the system, so the entropy change there should be negative. Okay, now what we want to do with entropy change is combine it with the other thermodynamic quantity we've talked about before, enthalpy, and combine them in a way that gives us this new term, which gives us some information about our system. The new term is called Gibbs free energy. And the Gibbs G is in there in the symbol. It's G, or again, we're always looking at a change, so it'll be delta G generally. But it's often just called free energy, even though it's abbreviated G. The Gibbs gets left off a lot when you're speaking about the subject. The change in free energy, well, this is one of the most common ways to calculate it anyway. The change in free energy is equal to the change in enthalpy for a reaction or a phase change possibly, minus the temperature, so that's going to be Kelvin temperature, times the change in entropy. Now, what free energy tells us is whether or not a reaction is going to be spontaneous under certain conditions. If the free energy is negative, so less than 0, we can classify that reaction as spontaneous. Now, some textbooks have changed from using the term spontaneous to the term favorable, because there is still an energy barrier that needs to be overcome, an activation energy to do a reaction. So for example, propane and oxygen, like when you light your barbecue grill, that is a very spontaneous reaction, but it doesn't just happen. You still need a spark or a match to get that reaction started. Now once it's started, it's going to go as long as you still have oxygen or or propane, but it's maybe a little more appropriate to call that a favorable reaction as opposed to a spontaneous reaction. Now, if delta G equals 0, that's a reaction that's at equilibrium. So that's important too. We can relate that back to what we talked about in the last few chapters. And if delta G is greater than 0 or positive, that means the reaction is not spontaneous in the direction written. But delta G shares the same characteristics of delta S and delta H. If we flip the reaction around, we would change the sign on the delta G. So if a reaction as written has a positive value, we could actually consider it to be spontaneous in the opposite direction from the way it's written. Okay. Now, the last thing I have here on this page before we get into some calculations related to free energy is another equation we can use to calculate free energy. We can relate free energy to the equilibrium constant. So if we know the equilibrium constant, we can calculate the free energy for a particular reaction. So the free energy is negative R. So this is the gas constant. In this usage, we want a different energy unit than liters times atmospheres. So in this case, we'll use a version of R that's in joules per kmol. And we'll actually see an example of this later on, Kelvin temperature and a natural log of the equilibrium constant. And we'll see how both of these equations can be used to determine delta G, to figure out whether a reaction is spontaneous or not, and to also identify maybe a temperature at which a reaction shifts to become spontaneous.